know what? Let's move. Hello! Oh my gosh, is that me? Here, finally? Hello, everyone. Hi. I'm so sorry for being so late. Got held up with something for a while, so I'm really sorry. I was checking in on my mama and everything. I'm sorry about that. But hello. I know, we're doing rat hours and this is perfect because we're gonna talk about sleep today. We're doing a rat hour stream talking about the effects of sleep. Wow, being sleep deprived. So this is actually gonna be perfect. Kept us waiting? Kept you waiting, huh? But... okay. Okay. I have my stuff here. Using this as ASMR? Oh, true. Wait, maybe I can make this relaxing. Wait. Let me put, what was this music? Oh my gosh, this is perfect! Our final biology lesson. How are we doing? I'll let people flood in because I started really late and just fucking spawned in with a stream. Are you trying to make me fall asleep? Yes, actually, the whole topic is sleep. So if you can make it through, you'll learn really cool things about sleep. If you don't, good night. Alright, I have my notes. How are you doing? I'm doing lovely, actually. Thank you for asking. I got to see my mama dragon today. I was supposed to show up. I was supposed to show up just to like literally download an app for her and show her how to scan documents with the app. You know, Adobe Scan, super helpful. I've used it a lot in my time. But yeah. You well in the future? Thank you. I really appreciate it. Yeah. I was only supposed to do that, and then I ended up yeah, I ended up doing a lot more than just that. So, like, shit, I guess. We ended up talking for a really long time about a lot of really important stuff, so I kind of got freaked out a little. But it was like a heart-to-heart, you know? It was like a good heart-to-heart. Hi, Suri, hi! Well, that's good. Yeah, like, I don't know. I'm good, don't worry. But, I've been good. I'm just gonna kind of let people flood in, if that's alright. Just give people a little more time. And as I kind of put my notes together and make sure that everything's okay. Okay. I'm sorry, I might be a little quiet for a little. Just because I'm just gonna sort everything. If that's okay? I'm really sorry. Alright. It's okay. I'm already passing out. Oh, it's okay. Like, you don't have to worry too much about what's it called? About moderating, if that's what you're worried about. It'll honestly be really fine. Usually these streams are pretty chill, so I can manage it. Okay, yeah. Hmm. Okay. Verb with noun? Huh? Wake up, wake up. Should I put different background music? Is that why? I'm sorry. Would you guys actually really prefer something else? I'm so sorry. I've been taking so long. I feel bad. I'm really sorry. I know that I shouldn't like. I'm sorry. But oh my god, I can't. I can't help but be sorry. You're always sorry. I know. I feel bad. I feel bad for not being like super duper prepared because I really wasn't expecting it to take this long. If you could bear with me for a little, I'd really appreciate it. Thank you so much.
I just wanted to say, for the short time that I've known you, you have brought so much joy and positivity to all of our lives. I hope that the next chapter for you is one that you are happy in and know that we all love and support you, _heart.
Oh, thank you. I really appreciate it. That's very sweet of you. Thank you so much. I really appreciate it. Thank you for the $50 super chat, Mr. YeoNwa. I hope that you guys are happy too. Honestly, really, I really do hope that you guys are happy with whatever that you encounter in the future. Okay. Alright, I think I'm just gonna organize these a little better because I just kind of have them as my like stupid random notes. I want to make sure I denominate them so that what is it? So that it's easy to digest because I'm worried that it will be like I hope that I wrote this in a way that's easy for everyone to digest. Because there's a couple of things in here that are a little complicated, but I feel like I can water this down really good. Sleep is one of those ones that you can water down really good. Pain is one of those ones that you can water down really good. I just hope I water it down pretty good. Okay, You got this, Suri? Thank you. I'll do my best today. Okay. So, I think I have this. Okay. As my short lecture on sleep. Alright. Okay, guys. It's neurobiology time. So most of the stuff that I've talked about in the past, you're gonna see a little cursor here. I'm gonna draw things out whenever I need to. Most of the stuff I've talked in the past was usually like regular, like just kind of like physiology. If anything, like I talked about heart contractions, and I talked a bit about like how neurons fire and stuff like that, but that was never like the deep neurology of things. So, one thing that I have to preface when we talk about this, because we're going to be talking about sleep, obviously, evidently. We're going to be talking, there's going to be a lot of this thing, and it's called an EEG. Oh god, I don't know how to pronounce it, so I'm really sorry if I butcher this and someone's like triggered by it, but it's a electroencephalogram. And practically is that it's like, have you seen those things where they like put like a cap on top of someone's head and it has like a whole bunch of little like, you know, little orbs and whatever, and they're all like connected and they're all like tracking different parts of the person's head? Okay, so that's practically the equivalent of what that is. So practically it tracks whenever like, to put it in simple terms, it just measures electrical activity. So obviously whenever your neurons fire, just think of it kind of as like a little, like a tiny little shock of electric activity. That's not really how it works, but just think of it like that. Because I'm not going to explain channels and everything right now. Okay. So how this thing works is that it's a lot like a electrocardiogram. Like the thing I told you about, like the... I'm drawing it completely wrong, but just that thing, you know, like the heart rate? It's practically like that, but it's with brain activity. Specifically in the cortex, but you don't need to know too much about that. Just think brain activity. So, when your neurons are in sync, it'll do nice big waves. And usually, what people tend to say is that it'll do it in low frequency and high amplitude. So frequency means like how often is it happening? Oh god, rat dog. And amplitude means like how big is the wave. So when all the neurons are firing kind of like in a synced motion, you'll have big large waves that are not very frequent. And then when there's a lot of different firing happening at different times, and this will become important later, it'll kind of be like, ooh, you, and that's practically telling you that there's a high frequency of things in very low amplitude. So a lot of different firing, but not synced. And that becomes really important, whether it's synced or not, when it comes to sleep. And usually these are denoted by like alpha, beta, delta, theta, gamma, whatever waves. But you don't need to know that. Just know that big, large waves usually happen at low frequency. Tiny, rapid waves happen at high frequency. And these are often used to know whether someone is asleep or not. So when it comes to when you're asleep or not, I just explained the like different waves. So what's kind of known in the brain, you have an area in your head, in your little skull. I'm gonna reach into it, bring it out here in front of everyone. You have something called the thalamus. Thalamus! Yay! Wait, I spelled that wrong. Thalamus. I forgot the A. And this thing likes to talk to the cortex. which is kind of like the big wrinkly kind of like just think of the big wrinkly part of your brain, and the thalamus is like really deep in your head. It actually more so looks like this inside your head, but I'm not gonna make it specific. So with this guy likes to talk to your cortex. And if you know much about the cortex, that's usually where a lot of the processing, like higher processing, happens. So stuff like, I don't know, what's a good example? Motor function happens in the cortex. Stuff like that. I don't think, should I explain the entire sections of the brain? I could briefly review it. Oh god. Okay, let me... Okay, I'm not gonna like go in super duper duper depth. But when you look at a brain, and usually it kind of looks something like this. And then you have like that. That's your stem. And it's just kind of like... Oh, that's kind of a really bad drawing of it. But it kind of looks like this, right? This is like the wrinkly part right here. And so you have like parts of your brain that like, this is the cerebellum right here. The back part of your brain here is the occipital lobe, so that's usually where a lot of like visual processing happens. You have like the frontal lobe, obviously. You have the temporal lobe. I believe a lot of auditory, if I'm not mistaken, processing happens. I think I need to double check. I don't want to feed you the wrong information, but I'm pretty certain a lot of auditory processing happens there. A lot of motor happens in the cortex and whatnot. And there's a lot of like manual, or not manual, automatic stuff that kind of happens in your brainstem. Like breathing, but there's like certain parts of the brainstem that works on, like, for example, sleep and wake, for example, but I'm not gonna go too far into that. I don't want to. It's too much work. Just know that, what is it? Kind of just like the squishy, wrinkly part of your brain on the outside is most of like the higher processing and function. So motor, whatever, like thinking, practically. Sometimes, like, for example, this is often where afferent information will go to be processed. Oh, sorry, like sensory information will be sent up there to be processed, and then usually you come down to the rest of the body to give like a command, like move your arm away from that fire. And so this guy, the thalamus, is super important because he is a lot of the relay between the lower brain, so all the automatic functioning, and the higher processing. So higher processing is just kind of like anything that has to do with processing information. Like you taking the fact that you're stepping on something sharp. I don't want to step on that. Well, actually, that's probably not the greatest example. Something is uncomfortable in my shoe. I want to stop walking to take the thing out of my shoe so I'm not walking with like a rock in my shoe. That's probably a better example. Pain is not really a great example because sometimes that processing happens in the spinal cord. But anyways, I'm not gonna get into it. Alright. So. So with this thalamus, as I said, he likes to take information and relay it to the head. Or like the higher processing. I say head because I just think of like the squishy part of my brain. But he is also known to be a quote-unquote pacemaker of sorts when it comes to like cortical, I guess, like rhythm, right? So going back to that EEG, it's like the constant waves. He's the one that does the syncing for all the neurons to fire at the same time. But the thing is, that happens when you're like unconscious. So you'll have long waves where like it'll be like synced and it'll be synced, and it won't happen very often. It probably won't look like this. I'm just drawing a wave to illustrate it. But when you're awake, because you have so much information going to your cortex, like I see something with my eyeball, I visualize it, it goes to like the occipital part of my brain, and then that gets processed, and it's I relay it somewhere, and then it comes back up. I don't know, auditory, I hear something, I process it, I react accordingly. You have so much stimuli happening that's overpowering whatever this guy is doing. So because there's so much stimuli happening, when you record the EEG, which is checking what the cortex is receiving, the cortex is no longer doing synced motions of neuronal waves, I guess. It's doing like a kind of thing. Right? So this has been proven in a lot of different ways. For example, mice are a very great example. So, have you ever seen a mouse whisk? If you know what that is. Have you ever seen a mouse sit still and its whiskers go? You know, I'm a mouse. I'm sitting here. I'm sensing information. And then suddenly, my whiskers start moving. Wait, I actually have a great way to do this. I'm taking in information. And my whiskers start moving a whole bunch. That's me taking in sensory information, right? So there's actually been studies where they've looked at the difference between a very active brain. So when a mouse is whisking versus when a mouse is quiet and its whiskers are not moving. So although that's not sleep particularly, it is an example of lower functioning, I guess, processing, right? And they did see a difference between, like, in the EEG, they did see a difference between how often, so how frequent, and how high of an amplitude those waves are. Now you're probably thinking, what the fuck does this matter? I don't fucking care about a mouse. I want to know about sleep. Shut the fuck up. And so, I come to you with, have you guys heard of REM sleep? No REM sleep or non-REM sleep. Have you heard of those phases? Like the stages of sleep and stuff like that? Okay, so more so in recent research, they used to say that it was 4 stages of sleep, but people have now grouped 3 and 4 together, so it is 3 stages and then REM sleep. So you have 3 stages of non-REM sleep. And if anyone knows what REM is, it just stands for rapid eye movement. Hi, Raiders! Hi, Zion! Thank you for the raid! Thank you! We're doing a biology lesson. Hi, Suri! Hi! We're talking about sleep! It's my final biology lesson! Welcome in, Raiders! Hi, my name is Slayer from Gen 3 Oracle, and there's Sleepy Sun Dragon! And it is nice to meet you if you've never met me before. If you've seen me before, I'm certain you know what's coming. But tomorrow, I will be graduating. But a little tradition, I guess, I used to have was doing little biology lessons on stuff that I've learned recently. So I'd like to share some of my knowledge today with everyone. And we're talking about sleep as your sleepiest sun dragon. Now, we were just talking about the stages of sleep. And there's something called an EEG, which is like kind of the same way as like tracking like heart rate, for example. And it measures how your your cortex, so like the higher processing, think of the mushy part of your brain, like the wrinkly part. It measures the electrical activity of that. Now what they found is that when you're awake, it was just like as I said, really rapid, really short little waves. Now you get to know REM sleep. You have stage 1. And then you have stage 2. And then you have stage 3. Yes! See, Sion knows! Sion is my best student, even though she knew this way before me. And then we have REM sleep. I'll get to what SWS is. But I have an EEG coming up. Whoa! I wonder why. But so practically super desynchronized, a whole bunch of rapid movement, very low in amplitude. But as you're getting to stage 1 sleep, you're starting to kind of slow down. You're starting to see like greater kind of spikes. They're starting to get larger, less frequent. When you hit stage 2, I probably shouldn't have drawn it like that. I should have probably drawn it more like this. When you hit stage 2, you're still kind of seeing kind of like similar like rapid activity, but you're starting to see like really large spikes, and they do have like kind of names, like the types of spikes they are, but I'm not gonna explain them because it won't be helpful. And then we hit stage 3, which is called slow wave sleep. And this is when you start seeing like the really big waves. Really large, infrequent waves. Lorg waves. Now this is usually slow wave, obviously. Slow, large waves. And this is characteristic of hitting deep sleep. Now once you hit REM sleep, you're starting to show characteristics of being awake instead of being asleep. Now the reason why people know that you're actually asleep during REM sleep is that you have a synchronization of rapid eye movement, for example. But you do experience rapid eye movement when you're awake. Another thing is complete loss of muscle tone. So you experience paralysis, and that's how people know that you're... Because they don't only do an EEG to test someone when they're sleeping. They also do different things like checking muscle tone, eye movement, stuff like that. Usually during stage 1, for example, they know it's stage 1 because you do something called, slow eye rolls. Slow eye rolls. So if you've ever seen someone falling asleep and their eyes are like kind of open and you see them do like the freaky thing where their eyes are like rolling in the back of their head kind of thing, that is characteristic of starting to enter sleep. They're starting to do slow eye rolls and it's really freaky, but that's how it be. So you start experiencing paralysis here. How to check eye movement without touching their eyelids? I believe you can check their eyelids, technically. I'm not 100% because I haven't looked into how they check eyes. Because I mostly focus on the EEG stuff. But I'd assume that they have some... either a light that they shine, or they just open the eyelid. Okay. So something that I think puts us into really good context between no REM sleep, or non-REM sleep, and REM sleep, is have you ever seen those videos of cats falling asleep, by any chance? Like where they do this thing where they do like the Sphinx pose, and they have their paws really, really close up to their chest, and they have their head up, and they close their eyes. Oh my god, rat dog. And then they do this thing where they slowly sink their head down. And sometimes they'll wake up when they're doing that, but they'll like do this slow sink down and then they'll like hit their face on the floor. And that is the difference between non-REM sleep and REM sleep. Is that cats do the Sphinx pose when they're in non-REM sleep, but once they start getting into REM sleep, they're starting to experience paralysis. So that's why their head slowly sinks and then it just touches the floor, or they wake up. Now when it comes to the sleep cycle, what often happens is that you have to descend. You have to descend the stages and then come back up on the stages to wake up. It is like characteristic, practically. So what it will do is that you'll start at awake, and I'm gonna add REM sleep here. And it's gonna be really awkward because didn't I just list that you have to go from non-REM to REM sleep? But just bear with me. And these are the 3 stages. This is all non-REM. Alright. So we have this nice... Let's make it like a little chart. So throughout the night... you started awake, obviously. And as you're starting to fall asleep, you hit stage 1. Sleep. So we're skipping REM. So I have not gone to REM sleep. I am just in stage 1. And then you practically go through a little period. And then you go to... like maybe it probably takes less than 10 minutes to traverse like between 1 and 2, I'd assume. And then eventually you hit 2. And then you fall down to 3. And 3 takes a bit. And then suddenly, throughout the night, you kind of start climbing. You go from like maybe 3. And then often you have a small stage of stage 2. And then you go immediately to REM sleep. And you have a first episode of REM sleep. And then you come back. And then you kind of come back down. And then you go back to stage 3. And you kind of have this thing where you keep going up and down over and over again. Like that. And then sometimes what will happen instead is that you'll hit REM sleep. But because it is so similar to being awake despite the paralysis, sometimes you'll have brief moments of waking. So that might be the time that you wake up in the middle of the night and you're like, I need to pee so bad. And this is your body choosing this period of like, oh, I'm in REM sleep, I'm kind of close, I'm just gonna wake up, smile. And that's when you wake up and you're like, yay, I gotta go pee. And you go to the washroom. And then you start back here. And you go through these cycles. And often, as you age, you start losing stage 3. And you go directly from 1 to 2 and then back up to REM. And you'll just stop experiencing 3. Sometimes later in the night, you stop experiencing stage 3. But your deepest sleep is usually like, obviously, the deepest sleep of no REM is your slow wave sleep, which is your stage 3. And then you hit your deepest sleep in REM sleep. I am just always tired, and I will talk about that now. Now that I've solidified how this wave works, right? And this is kind of crazy. So like, for example, like babies constantly just like start falling asleep randomly. Sometimes they immediately go to REM sleep. And people with narcolepsy have the exact same thing, where they suddenly just hit REM sleep in the middle of their day. If you heard of narcolepsy, it's like when you fall asleep midday randomly, often. And they just go straight to REM sleep, and that's why they experience paralysis sometimes. And I'll get to dreaming in a second. But people with narcolepsy also have an issue with hallucinations because of dreaming. And I will explain how dreaming works with all these stages too. Why we're never refreshed? Okay. Okay. So, now comes the question. What the fuck is this all for? You spend about, what, 1/3 of your life sleeping? And for what? And for what? What do I do this for? Oh, this is my favorite part. This and dreams. But I think the one thing that's been solidified is obviously sleep is needed. I think the person that has gone, Randy Gardner or something like that, the longest he's gone with sleep deprivation was like 11 days without dying. And you do die if you don't sleep enough, right? If you are kept awake for long enough, you can pass away because of it. So why do we devote so much energy into sleeping? Why is it so important? And like, this happens, like, why would like, I think everyone, like, if you think of it in an evolutionary stance as well, why would small animals sleep if they're susceptible to becoming prey to predators, right? Like, why is it so important that we'd sacrifice the possibility of dying in, like, an evolutionary standpoint just to get sleep? And even animals that hibernate, right? If you've heard of torpor, for example, some birds, some small creatures do torpor, which is practically like a state of, like, hibernation, where they lower their body temperature completely, and they lower their heart rate completely. But even during torpor, you'll have, like, spikes of just when they just wake up and exhibit slow wave sleep. They'll just randomly exhibit stage 3 sleep in the midst of, like, them in hibernation. And they'll have quiet periods, and then they'll just exhibit heating up randomly, exhibiting slow wave sleep, and then they'll return to torpor. Because torpor is not the same. Hibernation is not the same as sleeping. So, why? Should I don't think we need to go against unihemispheric slow wave sleep. There's some animals, like birds and ducks and stuff, that can actually have half of, just for a fun fact, unihemispheric slow wave sleep, stage 3, whenever I say slow wave sleep. Some animals, like birds, or like dolphins and stuff like that, will turn off half their brain practically. Half their brain will go into slow wave sleep, and the other half will be active and awake. And then they'll switch. So ducks do this, for example. They'll turn off half their brain, and they'll have, like, one eye open. And that one eye is making sure that there's nothing that's gonna kill them, but the other half of their head is, like, doing the equivalent of slow wave sleep. So this is exhibited in a lot of animals that migrate for long periods because they can't just keep swimming forever. This is exhibited in mammalial sea creatures, so like dolphins, whales, and stuff like that. Just a fun fact. Albatrosses do it. If you've heard of an albatross, they stay in the air for a really long time. But even, like, some humans exhibit this. But this is often if someone exhibits sleep deprivation. Their brain will kind of do... it's called the first night effect. Which means, like, one hemisphere would get less sleep depth than the other. That means that... Or... Was it... Okay, sorry. Scratch what I just said. I'm just gonna state what it is. I'm not too certain if it's because of sleep deprivation or if it's just a natural thing. But some humans exhibit the unihemispheric effect, and it's called the first night effect for humans. And practically what's been studied is that one half of your brain tends to wake up before the other half. And I'm pretty certain it's because of deprivation, that one half of your brain does not sink directly into the deeper stages of sleep, whereas the other one does. And that's why some people experience, like, lack of fulfilling sleep. But double check that. Don't take my word for it. I'm just sharing facts for fun. Okay, so now that I got all my funny little silly facts, why the fuck do we sleep ever? I know I'm still talking with this thing in front of me. It's on purpose because I'm gonna need it later, but I don't know if I should... Oh, you know what? I'll just hide it and I'll bring it out later. Okay. So, what's well known is that you have something in your brain, always going back to the brain, called the hippocampus. And, oh god, I can't flip the entire word, campus. And then you have your neocortex. I'm just gonna write cortex to not make it confusing, cortex. Now, in this example, your hippocampus's main purpose is short-term memory. So, what happens is that your hippocampus will have certain neurons that will exhibit firing with short-term memory. So, I don't know, something happens, your brain reacts to it. The hippocampus has different neurons that will talk to each other to form kind of like a short-term memory bond to kind of, and this is called synaptic, or actually, sorry, I'll get to that in a second. They kind of talk to each other and they solidify short-term memory. We're just gonna leave it at that. I don't want to explain too much. So it's storing short-term memory practically over here. And eventually, something called synaptic consolidation is that your brain will take this and go to the cortex, so higher upper processing, and it'll go and talk to neurons up here and be like, yo, I should actually distinct it with different parts of your cortex, because your cortex deals with everything from motor to auditory to whatever. And they'll talk to you and consolidate things like anything auditory. Or, yes, okay. Wait, am I getting this backwards? I might be getting this backwards. Let me think about this. Give me a second. Okay, no. Yeah, we're good. Alright, sorry. Okay, something happens. For example, hippocampus stores short-term memory, and practically what I should say instead is that it talks between each other. And this is called synaptic consolidation. They will all talk to each other, and they're practically just encoding with each other. So this will deal with anything auditory. This will deal with anything like, for example, visual. And this will be like spatial. Oh god, you can't see that. Just imagine that says spatial. And practically, the hippocampus will take the short-term memory, relay it over, and they'll all talk to each other, kind of solidify what happened, and keep it as like a memory trace, practically. And the memory trace happens in the hippocampus. It's just like, kind of, like I said, a storing of short-term memory. And kind of what happens is that if this, for example, event happens again, you get the same cue. I don't know, for example, oh, I feel like I feel a specific feeling in my shoe, kind of thing. Or I feel like a tag in my shirt. And I'm like, oh fuck, I remember this sweater. Like, I'm starting to retrieve that, oh, this sweater that I'm wearing has an annoying fucking tag. I consolidate the hippocampus, and the hippocampus will go and retrieve whatever memory I kind of had of that. And we'll start kind of storing it, in a way. So, practically what's happening is that because this is happening, and I have a short-term memory of it, it's sending things to kind of... What's the word? To kind of memorize it. It's like, oh shit, this is happening again. And it goes to the cortex and it starts storing it. Like, oh, for sure, I'm gonna remember this is like the reaction that happened the last time I wore this sweater. I gasped out loud about how annoying this was. I see the tag. I feel it physically. And practically everything is just kind of being stored. So a short-term memory is now being stored up in the cortex. And oh my god, I know this sounds like a lot of words, but I swear to god it'll become interesting. Now, this is called system consolidation. So practically, the short-term memory is becoming long-term. Now, what will happen the next time... And I'm just gonna get rid of all of this. What will happen the next time you have this experience is that rather than, oh my god, itchy sweater, and I go to the hippocampus to consolidate it, it will practically automatically go up to the cortex and tell you what's going on. So you'll kind of have the sweater and you'll go like, oh shit, wait, this sweater's the itchy one, and you'll take it off before you completely put it on. Thank you, Medicus. I'm sorry, I've been yapping so much, so I haven't been looking at chat because I'm like trying to get information out. And the reason why this is known, generally that there's like specific ways that it retrieves long-term memory and whatnot, is often like you can put a rat in a maze, for example, and certain parts of the brain will literally light up when tracked, when they're in specific parts of the maze. And your brain will literally store it. Like within the hippocampus at first. And eventually, what will happen is that you'll have this consolidation, so practically turning short-term to long-term, that happens during sleep. So when the mouse is awake, it'll rehearse like the maze while it's awake. It'll go through a maze, and certain parts of the hippocampus will light up. And it's like step 1, step 2, step 3. And, you know, you're rehearsing it here. Step 1, step 2, step 3. And it will actually go in a sequence. Your brain will memorize it in a sequence. The hippocampus will light up in a sequence. So this is what the memory trace is. Your hippocampus will have a sequence memorized as short term. Now what happens is that when you fall asleep, you'll start rehearsing the material in slow wave sleep. So in stage 3 sleep, this is where your brain is starting to store it in certain areas in the cortex. So your hippocampus is starting to store this in your cortex to kind of memorize the sequence for future use and keep it as a long-term memory. So another way, for example, this was kind of proven. The brain is so weird. It's kind of silly. Another way this was reasoned was that, for example, they scanned a hippocampus of like a mouse during sleep, and it lit up randomly. Like this one, like this part of the hippocampus lit up, then this part, and it was just completely randomized. Then they made a mouse go through a maze, for example, like I said, and scanned the mouse practically for like what would happen in the hippocampus as it went through the maze. And it did a 1, 2, 3 sequence. And then, during sleep, it exhibited the exact same 1, 2, 3 sequence during slow wave sleep. And there was even scanning in the cortex that lined up with sequential, I guess, firing that proved that there was like consolidation where they're like talking to each other. Okay, now that I kind of gotten the base down, I know it's confusing, but the way that I can water it down is that there's our stages of sleep, right? This is the last stage of sleep usually. This is the sequential stages of sleep. You go no REM from 1 all the way to 3, and then you hit REM sleep. And then often, I would hope that you'd wake up after. So, practically what happens is that you experience something, you memorize it in your hippocampus. So, hippocampus. You're experiencing something in a 1, 2, 3 stage. Once you hit stage 3, sleep, you start experiencing things in your hippocampus again in the exact same way. And it's rehearsing it. And while this is happening, it's starting to go and talk to your cortex as well to store it. It was talking to the cortex before, but now your cortex is starting to like embed it in a way that the next time you're put in this 1, 2, 3 sequence, or need the 1, 2, 3 sequence, it's already in the cortex. You no longer have to ask the hippocampus, quote unquote, for short-term memory. It's already turned it into long-term memory. Watering it down again, there's probably still some communication happening, but to put it into simple terms, basically it stores memory. Yeah, the hippocampus is your short-term, and then your long-term happens in your cortex. And this happens specifically during our slow wave sleep. Now, the theory is, and I love this, the theory is that when you're in these stages of sleep, your no REM sleep or non-REM sleep, it's been seen that these memories, the short-term memories that you're experiencing, are in bursts. It'll happen in bursts. It'll be compressed memory. It'll kind of be like certain sections will suddenly flash in, flash out. If you've ever been woken up mid-sleep and you can kind of remember a dream, but you can't really, and you can't recall all the details, but it was really weird and it was just sudden, and it was something that you had already experienced before. It was just like, I was having like a weird dream about like taking the garbage out or something like that, but it like, there wasn't really much to memorize about it. This often happens in these stages of sleep. And this is because what theory is that this is your brain learning how to relate the past to the future. So you have nothing interesting happening during these stages of sleep, because your brain is just memorizing what's happening. Like I said, in stage 3, your hippocampus is talking to your cortex to memorize certain things, right? So you're just rehearsing what has already happened, and you're just relating the past. Now, when you hit REM sleep, this is often where vivid dreaming happens. You're having full sequences, you have paced, like almost memory of your dream. And what people believe is that REM sleep is trying to experience or simulate the future. So your brain has now stored it up into the cortex when you hit stage 3 sleep. So you're storing in the cortex. Well, now that I have this information in the cortex, what do I do with it? Why is it important for me to memorize this during stage 3? And REM sleep introduced the fact that I'm going to take this information from the cortex and I'm going to try to apply it to the future. So if you've ever had a dream where you're in an exam, I hate these, I always get these dreams where I'm in an exam and I'm fucking failing because I didn't study anything, and I'm anxious and I'm like, I'm gonna fail this exam. Do you think I can take a peek at someone else's exam? Do you think I can dodge the exam? Can I delay it or something? And this is where a lot more emotion and stuff happens. Is that you're having more experience with actually applying this, actually living it in a sense, because it's full sequence and pace the entire time. And because of this, because of knowing what periods of these kind of memorizations or storing happens, what kind of dreams happen, they've actually done different types of tests to prove that there is a link between sleep and memory. So have you ever heard of the... Oh, I love this one. You guys remember the fucking thing from What's his name? Is it Dexter's Laboratory? Am I thinking of the correct thing? He says like something in French, and he accidentally plays it over and over again. What was it? It was some... Was it like... Was it Pomme de Terre? Amadou Fromage! Yes! So... The concept is that he was going to learn French. He played a recording, but the recording got stuck while he was asleep. And it just kept saying Amadou Fromage over and over and over and over again. No, that's actually partly true. There is truth to learning in your sleep. There have been times where they've done experiments where while someone is learning something, they'll expose them to either a sound or they'll expose them to an odor. And they will practically either replay that sound or, I don't know, disperse that odor during slow wave sleep, so stage 3. And when they're tested on it later on when they wake up, they actually have better test memory than, I was gonna say a wild type, but that's not really the correct phrase, than your placebo. And they showed that this only worked with slow wave sleep. You could only do that during slow wave sleep here. If you tried during it, like during REM sleep, it had no effect. If you tried it during stage 2, if you tried it during only waking, the odor didn't do anything helpful. But specifically during stage 3, slow wave sleep, there was better results of memory for an exam than any time else. And it's crazy. Because, like, for me, I'm like, holy shit, all those times that I've stayed up late for exams was so fucking useless. Imagine how much I could memorize if I was just awake during that. That gives you so much more motivation to get better sleep to memorize things. And this also ties in a lot. Oh my god. The sound on during the whole night would still impact you during stage 3? I think it would technically, but it's more effective if it was only during stage 3. Or else it kind of just becomes moot if you just have it all the time. Okay, what can I talk about next about this? And, okay, application time. So we talked about it. We talked about the different waves of sleep. We talked about how it works with memory consolidation. It's so hard to teach an old dog new tricks. That's coming. That's coming. Old people. My favorite topic. Yes. Old people. Okay. Alright. It's time to talk about old people and their sleep habits. Alright. You think that... Okay, so some old people don't sleep as much and they have poor memory. Okay, whatever. So why is it, like, actually devastating to not sleep? Like, sure, maybe someone will just have poor memory, but how does that actually physically affect someone enough to where they die? I'm not gonna give you the details of how cerebral spinal fluid works. All you need to know is that spinal fluid enters the brain at some point, and that is practically what bathes the brain. Your brain is practically floating in a whole bunch of cerebral spinal fluid-like stuff. It's not really called cerebral spinal fluid when it reaches the brain and the inside little wrinkly parts of the brain, but I'm not gonna get into it. You just need to know that it's like, it is technically cerebral spinal fluid. You need to wash your brain to keep it healthy, and that is true. That is 100% true. Because what happens during sleep is not only are you doing memory consolidation, what happens in your brain is that you have your artery, right? So this is where oxygenated blood is. And you kind of have something around it. Just call it a membrane. I'm not gonna get into it. And then you have your little brain cells, your little neurons. This is like a really funny way for me to draw him. You have your neurons. You have like kind of like their helper cells, like astrocytes that like to live near him. You have some astrocytes that will kind of hug the artery, but I'm not gonna draw that because you don't need to know that. He's everywhere. They're little helpers. And then you have the vein, which means deoxygenated blood. I don't know how to represent not oxygen. I guess I'm just not going to put anything. Vein. Artery. Right. So, the normal flow, and again, mostly theory, but cerebral spinal fluid will travel from... Okay, I'm gonna draw it in a different color. Blue. Ooh, my cerebral spinal fluid is covering where my blood is. This is where my blood is. And this is where my deoxygenated blood is. And my cerebral spinal fluid flows like this. Into this space. Why is it like right around the artery? It just is like that. I'm not gonna explain it. So you have cerebral spinal fluid that passes through your brain. And the rest of this area is the brain. Brain! Yay! So your cerebral spinal fluid will pass through your little neurons and everything, and it'll kind of do this towards your vein. Now the function of this is that when your brain, it eats a lot of sugar and energy. Like your brain loves energy. That thing consumes so much of your energy it's super important. Obviously, you know that. If you lose your brain, you're dead. So, how does it eat so much and then get rid of the waste that it makes? Because obviously whenever you eat something, something's gonna come out. So, your neuron is eating a shit ton. Nutrients. Nutrients. But then, it's getting rid of waste at the same time. Right? And you have these like waste particles everywhere. And it gets more concentrated, like the further you are from this source, obviously. If you think of diffusion. Whatever. And practically the cerebral spinal fluid will carry this waste into where the vein is. Or like near the vein. And practically, the thing is the artery comes in, the vein goes out. Right? If you think of it as like a circuit of sorts. So the artery is what's bringing the brain nutrients. So it's bringing nutrients. And the vein is what's taking the waste out. So, waste. And you're probably like, what the fuck is she saying? Why does this matter? She's just talking about brain waste and stuff like that. Most of this brain waste is actually cleared in deeper stages of sleep. So going back to my trusty friend over here, the deeper sleep that you get, the more waste is taken care of and disposed of. So when you get less sleep and you don't hit good deep like stages of sleep, or you only go through, let's say you only go through one cycle and then you wake up, or you go through 2 cycles and wake up instead of 5 cycles, for example. Let's say you go only down to here and then you're woken up by someone and you're deprived of sleep. You are actually concentrating a whole bunch of waste. Because it is so important that for some reason when you sleep, there's a higher level of brain waste disposal. And this actually has like connections to things like amyloid beta plaques, which is practically what causes like Alzheimer's disease. That instead of having these tiny waste dots that I showed, people that have And this goes into prions and stuff like that, but I'm not getting into that. Instead of having these little dots, they have giant plaques. They're like this, just these giant pieces of waste instead. And it makes it harder to get into the vein here. And it makes it harder to dispose of. And it does all sorts of bad shit. Where it inflames the... It practically, like, it inflames the astrocytes. Like, you have reactive ones. It activates stuff like your white blood cells in your brain. And that is not good when that happens. Those things can be kind of counterproductive. Not eating, does that mean you have a big brain? As long as you're clearing the waste. There's always balance to things, but practically. But, oh, sorry, let me give you... let me give you moderator. Hi! Practically, the less deep sleep that you're getting, the less waste that you're properly disposing of. And this is kind of the ongoing theory about why older people, for some reason, older people get less sleep or get less deeper sleep. So for some reason, older people do this thing. Instead of like going into stage 3 sleep, they'll just like stop at 2. For some reason. They'll just stop at 2. And they'll just skip 3 for some reason. And 3 has to do with memory consolidation. It's a deeper stage of sleep, so it means that it's getting rid of more waste. For some reason, they just do this thing where they're like, oh no, it's okay. What age is older? Like, I'm thinking of like, I don't know, like 60s, elderly. It probably just happens over time too. Like, just as you're aging, this happens. Like, it's not like as you're... Like, once you hit 60, you just stop doing stage 3 sleep. It's probably like as you're getting older, you like, oh, for some reason, this cycle didn't go down to stage 3, but this one did. And it just kind of happens degeneratively, I guess, in a way. And there's proven studies that for like some reason, being asleep has like it's been proven that there's this flow of cerebrospinal fluid during sleep. Because like when you're awake, for example, the theory and test that they did was they added a dye to cerebrospinal fluid here. And when a mouse was when a mouse was awake, obviously if it was dead, this wouldn't happen, but when a mouse was awake, it would only get this far, the dye, and then it wouldn't reach here, and you wouldn't see dye over here. But when a mouse was asleep, the dye would perfuse all the way down here, and you would start seeing it very concentrated over here, only during sleep. So, not only does sleep have a function of memory consolidation and keeping good memory, and the connection between, you know, the elderly not getting deep stages of sleep to have good memory, it also has direct conditions where it negatively affects, for example, your neurons, the waste management in your brain, which can lead to all sorts of different kind of degenerative disorders. And I guess getting to kind of like the last couple things about sleep, because oh my god, I kind of sped from that. I hope that it was somewhat understandable. Oh man, maybe this is a little complex. Yeah, I'm not gonna talk about this, actually. Oh, but this is actually so... I don't know, maybe this is a little too... You know what, we'll talk about it. It's somewhat interesting. I can wrap it up. I say hi. I'm sorry for not reading chat a lot and if I'm missing stuff. I'm just kind of talking about it. interesting so far. I'm so glad. I just want to yap about it. Maybe I'll sneak in a little stuff about pain afterwards, but... Oh, yeah. Alright, so we talked about whisking and brain activity. We talked about the function of sleep and memory consolidation. We talked about, for example, brain waste management. Really informative, thank you. What causes waking dreams? Wait, what is the definition of waking dreams? Occur while you're awake. Oh, generally, okay, so REM sleep. So REM sleep over here. I talked about it earlier, but REM sleep has a very similar EEG pattern. So it has the same brain. What's it called? Someone's drifting off to sleep, right? Actually, if it's someone drifting off to sleep, cause no, I was thinking of like when someone's waking up, but you know, I'll talk about that when I get to narcolepsy. It'll make a lot more sense when I get to narcolepsy. For some reason I was thinking of something else, but I will get to that in just a second. There's a lot of background before I talk about that, so I'm just gonna draw it out completely first. Same time next week? Yeah, haha, but I'm... okay. So practically what happens is that there is... Oh yeah, for all you comp sci nerds! There are circuits that work in your head practically to turn on and off REM and non-REM sleep. Because if I show... Oh, not that one. If I show this one, and you're wondering, okay, like how does your brain know to go from here to REM sleep? Or to go backwards from REM sleep to, like, all the way down? Like, how does your brain turn that on and off? How does your brain wake up? Like, if I'm asleep, how am I gonna wake up? Why doesn't it just infinitely go in a loop of going up to REM sleep, going down from REM sleep, going up to REM sleep? How do I actually wake up? So, I'm gonna draw this entire fucking circuit because it's like really annoying. But I'll draw it. Actually, I'll draw this one first. So we'll draw this out. So there's different... I'm just gonna draw... Just think of this as different parts of your brain. Because I'm not gonna explain the location in your brain and whatever. I don't want to. I'm lazy. Okay. So... Where is this? Okay, so you have something called the VIPOA, and that's your ventrolateral preoptic nucleus. Actually, wait. No, this one is actually okay. Wait. Run it back. Ignore what I just said. I'm talking about a different area. Okay, let me double check this before I say it out loud again. Because that one's actually... This is your what was it? Wait, no, I was right. Okay, I'm crazy. I'm insane. Okay, I'm fine. I was correct. Okay. It is your... Okay, alright. I was looking at the acronym and I was like, wait, that doesn't line up. But it is that. It is... Okay. This is your ventrolateral preoptic area. And this practically promotes sleep. So we're gonna talk about what keeps you awake and what keeps you asleep. And this is kind of just like... Okay, I'm gonna write it like this. Do not take it out of context. I'm gonna explode you if you do. This is your arousal system. It's like your brain stem usually. Brain stem. And your forebrain. I knew people are gonna be like, the what system? The what system? So oh my god. And then you have your orexigenic. Why could I not? Orexigenic. I was spelling it wrong because I was saying it wrong. Like, come on. Okay. And this is your hypothalamus. Orexigenic neurons. I'm just gonna put N dot. Okay. If anyone has done anything with circuits and knows what a flip-flop system is, this is a flip-flop system. So it does mutual inhibition on each other. So practically what happens is that this one will negatively affect the other one. And this one will also negatively affect the other one. So practically what happens is that when you want to be awake, you'll often have like a motivation. I gotta go to school. So you're oh my god. Wait, did I spell it right? Oh, it's orexin. Oh my fucking god. Okay, give me a second. I was like, wait, that's not right. Orexinergic. Okay, I did it right this time. When you have your orexinergic neurons activated, and usually this is because of a motivation to stay awake, so I need to wake up and go to school. Either like an alarm or something. This thing stabilizes the arousal system, which is practically the it's practically the wake up, awake state. And when this thing is super pumped, it's getting a lot of input here. This thing will super inhibit this guy. And this guy is the guy that promotes sleep, for example. And if you want to know, this thing releases stuff like acetylcholine. It'll release stuff like norepinephrine, histamine, whatever. It just releases chemicals. That practically means nothing. Me saying that, by the way, means nothing because all those chemicals are used a lot in different areas of the body for different reasons. So me just saying chemicals literally kind of means nothing, but just for your information. Now, practically what happens when someone has narcolepsy, which is practically it's kind of defined as the inability to stay awake during the day or during times you're supposed to be awake. They don't have this system. And when they don't have this, I'm gonna actually do that. If they don't have this, they don't have this positive input. So that means this can easily overpower and turn this off. And it just promotes sleep. And so the person just falls asleep. And it's literally been in brain scans that these neurons are just missing in people who are narcoleptic. And often what happens is that people who are narcoleptic, and this might happen for, so what you were saying was waking dreams. What I can say is that it's an often thing that happens in narcolepsy, and probably what's happening in the rare cases that happens to like a regular person, I guess, is that what happens in narcolepsy is that, oh, I love this chart. In narcolepsy, practically, you go directly from awake straight to REM sleep. So you don't do the proper thing where you go from awake to stage 1 to stage 2 to stage 3 to stage 2 to REM. You go directly, like, if I was to draw it on top of here, you go directly to REM sleep. You just go directly to REM sleep. And then you're awake. And if you remember what I talked about a bit ago, was that the most vivid dreaming, where you're trying to predict the future, and practically doing very slow, calculated, very realistic dreams, is in REM sleep. Like I said, in slow wave sleep, you do really fast bursts of random recalling of things, random whatever, very short bursts, memory recollection. Now, if someone has narcolepsy and they go straight from awake to REM sleep, they're already having that vivid dreaming immediately, going from awake to sleep. So this is the possibility of having hallucinations. And you can be technically still kind of aware and awake, but because REM sleep also induces paralysis, you're also paralyzed. So this is often what people also have, what's the word again? You guys should know this. This is like when someone's having like a dream and they can't move. Sleep paralysis. It's literally just called sleep paralysis. I forgot. Yeah, okay. Sleep paralysis. You're experiencing REM sleep and you feel as though like you are awake technically, but you're experiencing REM sleep and the rapid eye movement of being awake, but you're like at the same time you're still experiencing the paralysis. And this is often because like I showed on the diagrams, remember awake sleep has a very similar pattern on an EEG as REM sleep. They're practically equivalent. The difference is that REM sleep is often, you know, you're asleep, so you experience muscle paralysis, and usually the dreaming isn't while you're like cognitive in a sense. But because of the overlap, often there can be mishaps between them. So now going back to this. So now we know kind of what keeps you awake and asleep. So what establishes that paralysis then? That some people experience? So like how do you actually experience paralysis? So, and like how do you distinguish between REM sleep and non-REM sleep? So practically what happens is that I'm going to draw out a couple more circles for fun. And then, I don't know, for example, the amygdala is right here. Amygdala. Hey Suri, hi! I should write it on. REM off. Okay. So this thing positively influences that. Obviously, if I'm stabilizing being awake, I want to turn REM sleep off. I do not want to be in REM sleep, which is the deepest stage of sleep. Now, this thing likes to turn REM sleep on. So this is a sublateral dorsal nucleus. So this thing right here. And then over here we have the ventrolateral, and I think it's para-aqueductal or ductal gray. Yeah, I know. Bunch of what? And these are also a flip-flop system. So they have mutual inhibition, so one's on, one's off. And the amygdala likes to positively influence the REM on state. And this thing will go to things that can, like, turn, I guess, brain connected to REM sleep. Just anything that's kind of connected to the REM sleep cycle. And for example, that is like paralysis. Because what happens is that the way I can explain it is that there's positive, like there's encouragement to inhibit motor neurons. So that practically means that it's encouraging turning off something. And that results in something called atonia, which is paralysis. Okay. I think this is my last thing for today on sleep. Emotional stimuli. Okay. So, I drew out this entire thing.
Can't stay but hi Suri smile.
Hi man, thank you for the $5 donation. Okay, I know this looks like a lot, but we already went through this. So this is good, right? Promote sleep, wakes people up. This thing, if you have a motivation to stay awake, it'll encourage you to stay awake, which will inhibit you from falling asleep. Yes, you see, it's pretty easy when you look at it. Now, if you want to stay awake, we want to turn REM sleep off. So it encourages this part of the brain that turns REM sleep off. Wait, what's a color I can do that's like bright enough to distinct? Bright enough to distinct. Maybe like a bright pink? Oh, that's a little too close to the purple. Maybe like that? A hot pink? Yes! Okay. So, I want to turn REM sleep off if I want to wake up. It's a cascade. This thing turns REM sleep off. When REM sleep is turned off... when REM sleep is turned off, it's easier to wake up. Right? So. And I can draw it here, but it gets pretty crowded. This thing also just inhibits all of this. So if I want to promote sleep, this thing will inhibit all of these, but I don't know, I'll leave it for now. So, okay, let's start from... Why is it a line of codes? It really is! Let's start from... Okay. I'm waking up. I'm currently promoting sleep because I'm sleeping right now. I'm turning all these systems off. I want REM sleep on. I don't want you to wake me up. I don't want to be awake. So I stop all of these systems from working. Now suddenly, I have a motivation to wake up. I gotta get to work. I have a motivation to wake up. So instead of relying on this thing anymore, this thing is starting to encourage this thing, your arousal system, which will release a whole bunch of hormones to wake up your body. Alongside that, it'll tell this thing to fuck off. Shut up. And then when that thing shuts up, it stops inhibiting everything. It'll stop inhibiting, turning REM sleep off, which technically means it stops this thing. And now we have REM sleep off. I'm able to wake up, and I get with my date. Right? Great! That's practically the system that I'm talking about. So, when REM sleep is off, that you're more likely to wake up. When REM sleep is on, you're less likely to wake up. And again, these two inhibit each other. You can't have REM sleep on and off at the same time. Now, why did I add this? Why did I add emotional stimuli and the amygdala? Who fucking cares? What is this motherfucker doing? One thing with narcolepsy is that when something really intense happens, people who are narcoleptic kind of just fall asleep when they're overexcited. So let's say like you give a narcoleptic dog a treat. Sometimes a narcoleptic dog will receive a treat, emotional stimuli, and then it will just fall asleep. Why is it just collapsing on the floor falling asleep? Well, the amygdala encourages REM sleep. right? And that's why people with that have narcolepsy not only fail to have the wake up system, but they also immediately go into REM sleep. So they do the cascade I talked about, where they don't go and do the entire pathway down. They just go from wake to sleep and just become paralyzed. Faint and go, exactly. They just kind of faint. And REM sleep is directly connected to sleep paralysis, which is why they just kind of like are awake one moment, they get like, the dog gets a treat, and then it goes. And it's like, what the hell is happening? Now there's something called REM sleep behavior disorder. And that's another disorder where this doesn't happen. So specifically with paralysis, this is how sleepwalking happens. Is that you enter REM sleep, but you don't experience the paralysis. So you don't have sleep paralysis. And so this is how some people start punching the air when they're asleep. Or dogs that run in one spot when they're asleep. They fail to paralyze themselves during REM sleep, which is the most vivid type of sleeping. So REM sleep behavior disorder also plays into this, in a sense that they have a regular sleep-wake cycle, but because when their REM sleep is turned on, quote unquote, they fail to paralyze. And when they fail to paralyze, there's even things called, what is it? Like sleepwalking. I think that's called, it's like somnambulism, which is sleepwalking. And this happens at stage 3 as well. That they're kind of locked in kind of like stage 3, and they can enter REM sleep, but they don't go into paralysis. And there's even things like homicidal somnambulism, where some people have actually murdered another person in their sleep because they're having vivid dreaming. They're like entering the vivid dreaming state, but they're not having the paralysis. There's been people that have gone and gotten into their car while asleep. And there was an entire case of this because it was technically, criminal automatism? Or automatism? Where they're exhibiting states of being paralyzed, being asleep in the EEG. So they're experiencing, like, this cycle. But during this cycle, they're still able to move. And they're seeing things and interacting with objects. And there was actually a case where, I think his name was Kenneth Parks. But he actually murdered one of his in-laws. And he reported strange cycles of sleep. Where it would be like this, and then he would like spike up a whole bunch, and then come down, and then spike up, and it was just like a weird... It was like a weird pattern in in his sleep cycle. Like just constant awakening. But he was he wasn't paralyzed, but he wasn't, I guess, conscious. And it was like a whole case where he murdered someone and attempted murder of another person as he was asleep. And he actually, I believe he got acquitted because of that. Like he was not able to control himself at all during that. Try to behave in our dreams? As long as you're paralyzed during REM sleep, God, I hope. But, yeah. That practically wraps up all of that. So, went through a lot, honestly. Oh my god, I crunched that. Is there a treatment for this? Not particularly that I can think of. I believe it was... like... you'd have to somehow... like... I could assume that there's a way to trigger a neuron or hormone. It depends. Because, like, it could be a degenerative disease where, like, your neuron, like, the neurons that you need isn't there. Because narcolepsy is a degenerative disease. You're missing orexinergic neurons that cause you to stay awake. So narcolepsy is not directly treatable as it's, like, completely... Like, you are missing a core function of your brain. Lucid dreaming? I'm not too certain. Like, lucid dreaming definitely probably happens during REM sleep. I want to say that confidently. But I think when lucid dreaming happens, it's like... being aware of that state. I'm not too certain if it's like... I've never looked into, like, any documents about lucid dreaming, but... What is false awakening? Wait, give me a second. False awakening. I gotta search this up, because some of these things I don't know, so... Oh! Oh, I'd assume that false awakening is just like the dream within a dream. It's probably your body simulating you waking up, right? Because like I told you, REM sleep is like where the most vivid dreaming happens, and often it's in preparation, like in simulation of a future event. So you're probably simulating a future event of waking up, but then you simulate that future of waking up, but you're not actually waking up. You're kind of just tricking yourself. So like if you're having a dream inside of a dream, you're probably simulating having dreams during REM sleep. So kind of strange. Your brain wants to wake up, but you can't? I'm not too certain. That's like, I'd assume that like some people get locked in like, you know, like they're trying to wake up but they can't because they have to go through the cycles of sleep, but that's like my shot in the dark. In the class to flirt with the teacher, I ended up learning so much. But yeah, that's my nerd rant. You guys want to hear some stuff about pain? Really quickly? Before I have to go? Because I have to do something really quickly, but... Sure? Sure? Okay, here's my bonus knowledge before I have to leave. Okay. So, when you experience pain... This is my little nerd out that I learned today and I thought it was so interesting. There's two components of pain. Physical. I'm talking about physical right now. There's something called sensory discrimination, or being like sensory discriminative. So that means understanding the location of the pain. So is it my arm, my leg? The quality, so like how intense is it? Or actually, I guess quality is probably more so like what type of pain? Sharp, burn, that kind of thing. And then intensity, was it like fucking ah, or was it like ow? And that's the discrimination between all those kind of things. Now you have something called affective motivational aspect, which is practically the behavior of it. So you have fear, anxiety, whatever that comes from that pain, right? Will this be on the test? No. But practically what happens is that these are processed in different parts of your brain. So when it comes to the affective stuff, one is processed in your dorsal anterior cingulate cortex, so it's motivational, and your anterior insular cortex. And then for sensory, you have your primary somatosensory cortex, so, you know, sensory cortex. You have your secondary somatosensory cortex, and then you have your posterior insular cortex. All of these kind of take into account the feeling of pain, so the physicality of it. And the other ones was all about motivational or behavioral input, so pain, anxiety, whatever. Now, the thing that I found really interesting is that during hypnosis, you hypnotize someone And this is actually a thing. Like, it's crazy that hypnosis is actually, like, a medical thing. But in hypnosis, you can convince someone of the intensity or unpleasantness of pain. So during, like, functional brain imaging, you can have a hypnotic suggestion that a pain is more intense than it actually is. And what happens is that your brain in the somatosensory cortex will perceive the pain how it is, but then emotionally in the anterior cingulate cortex, so a certain part of your brain that emotionally processes pain, actually flares up a lot more if you're convinced that the intensity and unpleasantness is greater than you actually feel. So it's genuinely a thing where you can actually anesthetize, or not anesthetize, but like, you can numb someone through hypnosis. That your emotional processing of the pain can actually be dimmed through hypnosis versus, like, the standard numbing is obviously more effective, but those who are prone to hypnosis and whatnot, it can actually work. And it's crazy because there's things like asymbolia, which is someone who fails to display the appropriate emotional response for pain. So they can differentiate the pain, they can know that it's painful stimuli, they know it's sharp, or they know it's burning, they know the location, they know the intensity, but they're just like, it doesn't hurt, I don't feel it, it doesn't hurt. And that's also display of that kind of disconnect in the effective motivational behavioral section of your brain. Now, okay, really quick rant because I actually have to go soon. But this actually has a connection in a theory for humor and the evolution of humor. So this is called the false alarm theory, and I thought it was really interesting. And the false alarm theory is practically that there's two key requirements for laughter. There needs to be a sense of pain or danger, followed by pain being no longer aversive, so the false alarm. So have you ever, like, seen a baby trip and fall on its face and you're like, ah! And then the baby gets up and is smiling and giggling and you're like, oh, silly baby. So that's an example of people believe that the theory is that you perceive something that could be dangerous, but then it turns out it's not dangerous, and so you laugh. And some people believe it's because, like, for example, have you seen, like, when dogs or animals are angry or like sense danger and they start, like, baring their teeth and going like, "Rrr, rrr." And then if it's not something bad, you just kind of like and people believe that's why you smile, for example. So you need to sense some sort of danger and then have a false alarm for it. And this can actually be tied to social aspects. So, actually, social rejection, crazy jump, but social rejection actually processes in the same emotional spots as physical pain. So you know how I told you that there's two parts of physical pain? There's the physicality or sensory discrimination in certain parts of the brain, and then there's the affective motivational aspect or behavioral aspect that are in different parts of the brain. So the dorsal anterior cingulate cortex and the anterior insular cortex both are activated during a social pain. So, you know, something that has to do with social connection or social value, rejection, exclusion, etc., etc., etc. And practically what happens is that you have the same, like, flare-up response as you would for physical pain in the emotional processing centers. And I don't know, it's pretty interesting because that then ties back to humor. and laughing. So maybe the sense of danger, because there's 2 key requirements, you need to sense danger and then you need to have a false alarm for laughter. Maybe the sense of danger is taking that risk to make a joke, or taking that risk to make fun of yourself, or taking that risk to say something outlandish or do something stupid or silly or whatever. And then when you see that people have a good reaction to it, and it wasn't adverse or it wasn't, you know, embarrassing or whatever, you get the false alarm feeling and you laugh, and everyone laughs because they're caught off guard, and then they realize it's fine, and then they laugh. So, I don't know, I just found that theory really interesting. You can search it up if you want. The false alarm theory, I don't know, I found it interesting. Especially tying into the fact that certain parts of the brain are activated as well when it comes to social pain. And this was actually, oh my god, this shit was so funny reading about it, I'm sorry. But they did a study where they had like... Okay, so they had 3 people, right? In like a computer simulation. Right? This is like 2 different instances of it. In a computer simulation, there was like a ball being thrown. And like, this is you. You're the player. You're player 1. And practically what happens is that they told you that there's 2 other players. So there's player 2 and player 3. Right? But actually, player 2 and player 3 aren't real, but they didn't tell you that during the experiment. They're not real people. But what they did is that they made you pass a ball around. And they would pass the ball around like this. Like in a circle, right? And you would be included. And they made the AI pass the ball around just between the 2 AI and exclude the live test subject that was sitting in front of the computer. This was their experiment on the person. And this actually caused the anxiety to it mediated the behavior response in physical pain. The same way, the feeling of exclusion activated those same parts of the brain. Like, as physical, like the response to emotionally processing physical pain. And it's actually been seen that social distress is proportional to activation of those parts of the brain. And it's actually been seen, and this is probably why, for example, people get addictions to opioids or analgesics, is that analgesics and opioids and stuff like that, like Tylenol, whatever, actually dim the amount of pain that is experienced. Like the social pain that's experienced as well. Now, I'm not saying to just fucking eat a whole bunch of... Like, if you're feeling bad and you just fucking take Tylenol for fun, don't do that. Because there's a lot of downsides to that. And there's a lot of much better medications that could be applied to situations where you're feeling distress. But just as like a thing for people to know, because I think a lot of people have this misconception of like, why do people get addicted to like opioids or Tylenol or whatever? And it's this connection. It's this connection of not only stumping physical pain, but it's stumping like a social pain that happens. So, I don't know. I think it's something always to be mindful of, to never overlook. But it's not fun to be just, oh hell no. Ghosted, time to bust out the trauma. Oh my god, no, the trauma doll. But I just wanted to share that because I thought it was really goofy and I learned it recently and it was, I don't know, I enjoyed it a lot. I was thinking about the false alarm theory. Like, I often make fun of myself, and then when you guys laugh about it, I feel relief, and I'm like, oh yeah, that was funny and silly. I took a risk, and now I feel false alarm, and now I feel relaxed, and it makes me giggle. But obviously, it's just a theory, but... I see it. I see where they're coming from. But, okay. That was my spiel! My last, final... whatever. SNRI? Yeah! Wait, SNRI? Sorry, I was thinking SSRIs. Same time next week. But I hope that you guys enjoyed. I hope you learned something. I hope it was interesting, and I hope I delivered it decently interesting. Sorry if it was a little messy, or if I mixed up stuff. But that's a lot of the stuff that I've taken in so far recently, and I found it really interesting, and I just wanted to share it with everyone. I learned a lot. Now I'm a super big brain. Thank you for the $2 super chat. I appreciate it. Thank you, Onyx. Very informative. Yay! I'm sorry for being so late today too. I do have to scramble like ASAP because I have to complete something. I have to complete something before the end of the night. So I'm gonna go do that. But will you stream on 3 unique? Gonna miss them? One day. But yes. Alright. Thank you guys for tuning in. I hope that you guys enjoyed it. I hope I was able to answer some questions. I hope that you get good sleep. Get good sleep. That's important. Gosh. Obviously, evidently, especially for you old people. Ugh. Ugh. But yeah. Okay. Would you be interested in becoming a professor? Probably not. That sounds like a lot of work. Thanks for everything. Thank you for tuning in. Thank you for the 2 months. I don't know. I've heard a lot of things about professors. And I've heard that, like, becoming a master's student is, like, the most stressful, horrible, evil experience ever. And some people need to, like, learn to recover from them. Like, from being it. So... Okay, should I... Okay, Chiaki's still streaming. I'm raiding Chiaki. I'm gonna get her ass before she logs off. She's been streaming for a while, but thank you guys for tuning in. As I said, make sure you eat, drink water, get some rest if it's appropriate time for you. Make sure to, of course, always face the sun. Oh, Suri, for those who have the rest of the day ahead of them. Oh, yeah, Suri, for those who are heading to bed. Get good sleep, and I hope that you learned something fun today. And I'll see you tomorrow. My graduation's tomorrow. Also, we never got to do Sun Elders Uno. So let's do Sun Elders Uno. We'll try to sneak it in. I think we sneak it in maybe like right before, like maybe an hour before graduation. We'll do Sun Elders Uno. Graduation Uno? I don't want to do it during the graduation because I feel like that's a little evil to be like, only Sun Elders. So, I'll sneak it in like an hour before, okay? Thumbs up, thumbs up. Alright, I gotta go now! Okay, bye everyone! Thank you for tuning in! I hope that you enjoyed! Bye bye! Bye 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 bye! Bye bye! Bye 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 bye! I'm so sorry for being late again. I'm so sorry. I'm sorry! But I hope it was still entertaining, and I hope that you learned a lot, and I hope that you enjoyed it, and I hope that you have a good day, and I hope that you rest well, because you need the rest. And now I'm always super self-conscious about how much I sleep and when I'm sleeping. And this has actually probably changed the trajectory of my life forever. I hope it positively changes the trajectory of your life forever too. Okay, bye bye!